Well, now, according to the Bohr model of the hydrogen atom, electrons can only exist in one of, well, Bohr thought 7, but actually we now know it was 7, but he thought 6 possible energies. And he designated those possibilities of energy as n equals 1, 2, 3, 4, 5, 6, and 7. We can visualize it this way. N equals 1 would be considered as close to the nucleus as the electron gets, otherwise known as the ground state. And that as electrons absorb photons of electromagnetic radiation, they can be excited to higher and higher energy levels, but that they cannot exist in between those levels. So, of course, that means they can only absorb certain amounts of energy, and when they fall from excited to lower energy states, they emit very specific amounts of energy as photons in very specific wavelengths. So, based on what he could observe from exciting hydrogen atoms, this was a very good model indeed. He also believed that the electrons can only exist in one of those possible orbits, and that the electrons orbited around the nucleus, much as a planet would orbit around a star or the moon orbits around the Earth. But of course, that was a fairly primitive model that couldn't explain the observations in other more complex atoms. So that's where the quantum model was later established. And much like the Bohr model, even in the quantum model, electrons still have only one of 7 possible what we call principal energies. Namely, there are going to be far more energy possibilities in the quantum model, but still there's a finite number of them. And there are 7 what we call principal energies. And sort of in respect for Niels Bohr, we use the same symbol, little n, and designations of 1 through 7 to indicate which of these principal energies we're referring to in an atom. Now, each principal energy level contains electrons that may or may not have the same energy. In other words, even within an energy level, we have different possible sublevels of energy that are designated as S, P, D, or F sublevels. Now, there's many possible sublevels as the number of the principal energy level you're talking about. In other words, if I'm talking about the 3rd energy level, then there are 3 possible different energies an electron could have. We're going to see there's an S sublevel, a P sublevel, and a D sublevel in the 3rd energy level. On the other hand, if we were talking about the 1st level, there's only one possible sublevel, and we're going to see that it's the S sublevel. So that's what I mean by there's many sublevels in an energy level as the number of the principal energy level itself. Now, the big difference between the two models is this one here, that electrons don't exist in little circular orbits, but rather they exist in what are called orbitals. And it's a terrible, terrible misnomer when you get right down to it because of the first 5 letters in the word. But an orbital is not a circular path around the nucleus taken. Instead, it's a space. That's all it really is. It's a 3-dimensional volume of space located somewhere around the nucleus of the atom. Now, worse than that still, it's a statistically probable space. In other words, we visualize them as existing even if the atom is not built to our own liking. And these statistically probable spaces are where you could expect to find an electron 90% of the time if it quote-unquote lives in that orbital or is designated for that orbital. We're really talking about a space where you could expect to find it 90% of the time. For instance, if my teaching assignment were at a school where I had both a classroom and, say, an adjacent office, now you might consider all of this my orbital, because if you came to find me on any given day, chances are 90% of the time I'm going to be located somewhere in this orbital. Now sure, it's subdivided into two separate spaces, but nevertheless it is my one orbital. It is where you could find me 90% of the time. And that's very different than the Bohr model, which believed that electrons simply circled at fixed distances from the nucleus. Now, what do these orbitals look like? Well, this is what they look like. The simplest type of orbital and the lowest energy. These are listed in order of increasing energy. Electrons that live in these orbitals have less energy than the electrons in these, and so on and so forth right on down to the end. But these S sublevel orbitals are simply three-dimensional volumes of space centered on the nucleus of the atom, which I can picture as at the crosshairs of these three axes to give it three-dimensional appeal. And the electron assigned to this orbital would be found somewhere in this spherical volume of space 90% of the time. Where exactly, you can never tell. And where is it the other 10%? No idea. Now, these p sublevel orbitals, which some people call bilobed, because it's like my previous example of office and classroom, it looks like two different spaces, but in fact, this is a single orbital, a single space in which you could expect to find an electron 90% of the time if this was that electron's orbital. It may be over here or over here, but it's going to be somewhere in this space total 90% of the time. Now, P's have more energy than S's, but even higher energy sublevel orbitals are called D sublevel orbitals. And they have these shapes, four of which are pretty similar. Namely, they have four lobes to them. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then you have this weird outlier that has a couple of lobes and a donut-shaped ring lobe. And these d orbitals all have equal energy if they contain electrons. However, they are all higher energy than s or p sublevel orbitals. Now, the oddballs are these f orbitals that have the highest energy of all in a given energy level, principal level. And they have various shapes that are fairly complex, and we don't need to bother to really know, but we do need to know that f orbitals contain electrons of the highest possible energy. Now, please notice the numbers, because these numbers are accurate here. If you're talking about an s sublevel, there is only one space in that sublevel, one orbital. If you're talking about p's, well, then we've got three spaces. Talking about d's, well, you're looking at 5. Talking about f's, well, you're 7. And yes, there's a pattern, 1, 3, 5, 7. If there were a theoretical next higher sublevel, then you'd expect it to have 9 orbitals in it. Now, why is this so important? Well, it's because up to 2 electrons can inhabit the same orbital. No more than 2, however. And we're going to see in many cases some of the orbitals are empty, or they have just one lone electron hanging out in them. But you may have up to 2 electrons in any given orbital. Now, why is that? Well, it's because of the behavior of electrons. First of all, we know they are negatively charged particles, and you would expect 2 negatively charged particles to exhibit an electromagnetic repulsion. In other words, there's no way they're going to peaceably coexist in the same orbital, the same volume of space. However, electrons spin, and they spin in either clockwise or counterclockwise directions. One of the two types of possible spins. And spinning charged particles, like electrons, generate magnetic fields with north and south polarities. So, of course, if I had an electron spinning one way and it generated a north and south magnetic pole, and I had another electron spinning in the opposite direction, it would generate a south and north magnetic pole. So if I had 2 electrons, sure, they're negatively charged, they wouldn't like to hang out in the same volume of space, but if they had opposite spins, they would generate these opposite magnetic polarities. and there would be just enough of a magnetic attraction to almost overcome the repulsion between the two charges. Now I say almost because the electrons would prefer to occupy separate spaces if they might. But if they have to hang out together, if they have opposite spins, they can occupy the same volume of space. And therefore, that's why I say we can have up to 2 electrons in a given orbital. Now, here's an interesting situation when you start looking at the energy levels and their sublevels. In the first energy level, we already said there's many sublevels as the energy level they're in. So there is a 1s sublevel. Now don't forget, an s orbital is only a single space. And therefore, in the first energy level, close to the nucleus, there's room for only 2 electrons. Because if this is the only sublevel, and there's one orbital, and we can put 2 electrons in an orbital, there's room for only 2. Then, of course, if we move outward, away from the nucleus, there's more space. We have more room. And in the second principal energy level, there are 2 sublevels, S and P. Now don't forget, an S sublevel has only one spherical orbital. If I back you up and show you, there it is. But if you have a P sublevel, there are 3 spaces in which electrons can hang out. 3 orbitals. Excuse me. So if we have 4 orbitals in the second energy level, we could accommodate 8 electrons in 4 orbitals. So yes, the second energy level has a capacity to hold 8 electrons. If you move out to the third energy level, there are 3 sublevels, S, P, and D. And of course, an S sublevel has only one sphere, one spherical orbital. It has 3 of those bilobed orbitals. And a D sublevel has 5 of those mainly 4-lobed orbitals. And don't forget the orbital with the donut. So that really means in the third energy level, there's room for 9 orbitals. And that means this level could accommodate 18 electrons. And this is the pattern that continues. In the fourth energy level, you have all 4 sublevels, S, P, D, and those high energy F electrons. So of course, with 1 orbital and 3 more, and 5 more, and 7 more, that's a grand total of 16 spaces way out there in the fourth energy level, and we could accommodate 32 electrons. Now, we're going to see that in the fifth level, you would expect there are 5 sublevels. And in theory, there are. There's an S, a P, a D, and an F. And then you go alphabetical from there in terms of theoretical sublevels. Theoretically, there's what's called a G sublevel, EFG. And this theoretically, of course, holds 1, 3, 5, 7. And if a G sublevel existed, it would have 9 spaces, 9 orbitals. And that would be a total of 16, 24, 25. And 25 orbitals could hold 50 electrons. But as we're going to see, no atom is big enough to need those spaces. In the sixth level, well, you do have S, P, and D sublevels. But there's a theoretical 6F, a theoretical 6G, and a theoretical 6H, which could hold or has 11 orbitals in it. And those 11 orbitals could hold another 22 electrons for a grand total of 72. But again, no atom is big enough to need all space for all those electrons. And then theoretically, out in the seventh level, there's an S, a P, theoretically a D, a F, G, H, and even a theoretical I sublevel. And it would have, well, 1, 3, 5, 7, 9, 11, 13 orbitals for an additional 26 electrons, a whopping 98 total. Now, if you add all this together, you'll get far more than 118 electrons. And the biggest atom has 118 electrons. So you see, many of these spaces are theoretical only. These are the ones that actually exist in atoms. And we'll continue with the next recording.